Okay, so we just looked at polar coordinates, but for the special case of motion in a circle, and we developed these three key equations for position, velocity, and acceleration. Now let us look at first polar coordinates and then tangential normal coordinates in a manner that they generalize motion in a circle. So let's actually first look at polar coordinates as they are closest to the thing that we just saw. This is polar coordinates for general motion in 2D. Okay, so let's say again that we have some axes and we have some motion like so, which is not circular, certainly, and we have some point. We have the angle theta defined as usual and the radius r like so. This is point P, okay? Let's see if we can reproduce this image. Okay, I'll just reproduce that image. And then let me now draw coordinate axes on this thing. So the ER coordinate axis is basically this direction, and then the E theta direction is this, and E theta is defined as being perpendicular to ER and is in the direction of increasing theta. Basically, it will be in sort of going in the anti-clockwise direction because theta is defined to be increasing in the anti-clockwise direction. Okay, so sometimes people put these little arrows to indicate how theta changes, but that's the direction of increasing theta. Okay, so that's it. That's polar coordinates. R is still the distance between point O, the origin, and the point P. Theta is still the angle made by OP with respect to the x-axis. Okay. And ER is along OP and E theta is perpendicular to OP. Okay. That's polar coordinates. I'm not going to derive the formulas, but basically the formula is analogous to this acceleration and this velocity. I'm just going to write down what those things are. And then we will briefly look at what the meaning of each term is. So position vector R, that is still RER. The velocity vector V, it now has two terms, right? Previously, the velocity had only one, it was exactly along E theta direction, so it only had a E theta term. There was no velocity component along the ER direction because, well, it was moving along a circle, and ER was perpendicular to the tangent to the circle. Whereas here, you can have an ER direction as well as an E theta direction because this ER is not perpendicular to the motion direction. It's just along this direction, okay? So V has two terms. It can have a R dot ER and then R theta dot E theta, okay? So this is motion along ER. This is motion along E theta. When we say motion, we really mean velocity along. So along the ER direction, if the radius, this thing changes, that R dot is basically the velocity sort of in that direction. It's R dot ER. And then in the perpendicular direction, it's r theta dot e theta, which is the same as before. Okay, so that's position vector, velocity vector, and then acceleration a. Now instead of having two terms, it has four terms. It looks like this. So this is along the ER direction. It looks like this, plus, and then along the E theta direction, it looks like this. Okay. This term, like we discussed, is still called centripetal acceleration. This term is just due to the rate of change of the radius. So if the radius changes and the rate at which the radius changes, you have an acceleration along this direction. And that's basically r double dot er. So there's no special name for it. And then there is the term for, let me just put it on the other side here. And then there is a term reserved for this other acceleration term, which is called Coriolis Acceleration. And that is basically your 2 theta dot r dot or 2 r dot theta dot. This term, that's basically this term, which is a new term, is called Coriolis acceleration. So you can sort of try to look up why it's called Coriolis. In any case, you can derive this expression by differentiating this and using chain rule, basically your product rule for r dot and er and etc. You will get these four. Each of these will give rise to two terms, and that's why you have four terms here. And then also, I guess I'll leave it at that. Notice that unlike motion in a circle, where we use this capital R or uppercase R, here we are using small r, lowercase r, to indicate that big R is actually a constant because you're moving in a circle. Small r is not a constant. Potentially it can change. And I guess you have r double dot and r dot and so on, which will be 0 if it was a constant. And because it need not be a constant as it's moving along in this complicated curve, you have those terms there. And if you want to go back to your old expressions for motion in a circle, you just set those derivatives to 0. So if you set r dot and r double dot equal to 0, then you have the old equations. Okay, so that's really about polar coordinates. One additional sort of piece of information is if you want to convert polar to Cartesian, the key equations are as follows. So this is ER, this is E theta, this is theta, this is theta, right? And then if you have I like so, and J like so, this is converting so this, you can use the following equations to convert from polar to Cartesian or Cartesian to polar. Basically you have ER equals, so ER is this, its projection onto the I direction is, what is it? So if you drop a perpendicular here and say what is the component of ER along the I direction, that's going to be equal to, so you can write this as component times I plus component times J. Its component along I is basically cosine theta, and this is sine theta. And for E theta, It's similarly, you can write it like this. Its component along the j direction is in fact cosine theta. Its component along the I direction is sine theta, but it's along the negative direction of I, so it's actually minus sine theta. Okay, so you can draw little triangles to cosine theta, sine theta. That's one thing, and then for this guy, it's sine theta, and then minus something like this. Okay, so t theta, and this is ER. Okay, so that's how you convert from Cartesian to polar. So if you're given some vector in polar, you can just plug in these equations to convert to Cartesian. And similarly, you can show that it turns out it's cosine theta ER minus sine theta E theta, and cosine theta ER plus, so if you take these two equations and rearrange them, you can get these two equations. Basically, take these two equations and solve for I in terms of ER and E theta, you get this, and solve for J, you get this. Okay. To solve for these things, you can sort of multiply through by cosine theta and sine theta and cancel things and so on. Okay, so I'll sort of let you think about it. If it's not necessary that you know the proof of this, but it's good to know these formulas or these transformations. Okay, so that's about polar coordinates. That's all the formulas there are. Next, we will look at tangential normal coordinates. Okay.